let us start. So, last lecture we discussed the competent scattering. Okay, so with that example, essentially we covered all the tree-level diagrams in QED. So tree-level diagrams means those does not involve in loops. Okay. So so far, encountered diagrams which are which are called tree-level without loops. Okay. So these are called the just tree-level diagram. Okay. And so now you should be able to actually treat all possible tree-level diagrams. Okay, you already have all the tools to treat all possible tree-level diagrams. But tree-level diagrams actually there are many important things missing just in the tree-level diagrams. Okay, so now let's today we will talk about how to go beyond that. So we talk about quantum fluctuations. So this is a very big subject, and actually will consist a big chunk of quantum field theory too. So here it's more like just to give you a preview of the basic idea of the subject. Okay. So one feature of the tree-level diagram we have encountered. So if you want to summarize the, say, features of tree-level diagrams, what would you say? Yeah, other than no loops, other than looks like a tree. Yes?
There's like no free momentum.
Exactly. So the key is that all intermediate momentum say in all propagators, okay, all intermediate momenta, they are determined from external ones. Okay. So when you treat the tree-level diagram, there's no momentum integration. Okay. So this looks like a very simple mathematical feature, but actually it turns out actually there's a profound difference. Okay, when you include both mathematically and physically, when you include the loops, and there are profound differences. And also, you can show that the so now let me just summarize. So now when including the loops, okay, there are many new features, okay, arises. And so let me just first give you some simple examples of the including loops. So let's just consider the say, for example, one is just consider the electron propagator, and it's just a line, okay? But now you can consider adding a photon line here. Okay, adding a photon line here. So this is like the process, and now you have a loop. Okay, it consists of this photon line and this electron line. And so you can consider this as a process like electron propagate, and then can emit a photon, and then it absorbs itself. So this photon is purely virtual. Okay, it's purely virtual. It does not. It's purely a virtual photon. But such kind of process actually affect the propagation of an electron. Okay, so you can view this photon as something fluctuates from the vacuum. Okay, so you can imagine this comes from the vacuum fluctuations. So this is one process, and another simple process if you consider propagation of a photon, and then the photon can actually break up, say, can pair create an electron and a positron pair. Okay, and then this pair can annihilate again, and then to form another photon. So this is just like, again, this is like a correction to just a simple propagation of a single photon. So initial state is still one photon, and the final state is still one photon, but something happens in between. Okay, and again, there's something happens in between. You can interpret it as some kind of vacuum fluctuations. Okay, so both electron and positron here are completely virtual. Okay, there's no real electrons you can detect. So the third simple process is this one. You remember we have the electron and the photon interacting vertex. Okay, so this is IE gamma mu. Okay, so this is the electron and photon interacting vertex. And this vertex can also be corrected. So imagine you have a photon. So imagine the electron when it comes to, and then first emit the photon, and then get absorbed by the electron which comes out. Okay, and so this will correct the vertex. And so this is called the vertex corrections. So these two corrects the propagator, and this one is the correct the vertex. So these are the simplest loop diagrams. Okay, these are the simplest loop diagrams. In each of them, here just there's a single loop, and then there's a momentum, a free momentum in the loop. So you have to integrate over the momentum in this room because it's no longer determined by external momentum. Okay, it's no longer determined by external momentum. So it turns out such kind of momentum integration. So if I call this, say, momentum k, okay, and then you will involve in so let me first talk about the mathematical features. So mathematical real features for the loop diagram. So the mathematically now is you need to integrate over the internal momentum. Okay. So now you need to now you have some free momentum to integrate. So this may look like something just very, you may say this is not a big deal, but actually this turns out to be a very big deal because this momentum, this integration, just by definition, is from the you integrate over all possible momentum. So k is so each k is integrated from minus infinity to plus infinity. Okay. So in particular, this includes the region that k0 can go to infinity, and the magnitude of k can also go to infinity. Okay. So we include those regions. So if you have this kind of infinite range of integrals, then there's a possibility you get divergence. Okay, there's a possibility you get divergence. And in fact, that divergence do happen, and happen almost everywhere. Okay, whenever you look at loop diagrams, you always, essentially always find the divergences. So so this leads to divergences. And such divergences are now more complicated. It's not like the simple divergences we already considered the various we already seen various divergent quantities, and so far those divergent quantities can be treated in a more or less simple way. So you either subtract the infinite constant, or you multiply by infinite constant. Okay, and in the case when you multiply by infinite constant, you can always take the ratio, and then those infinite constants go away. And or you can just subtract the infinite constant, redefine your energy, redefine your charge, etc. But in those diagrams, the divergences are much more complicated because they come from doing some integration of some complicated expression. Okay. And so those divergences cannot be simply removed by you just add a constant or remove a constant or just multiply by a factor. Okay. So they cannot be removed. In general, cannot be removed simply by, say, subtractions. Removed by simple subtractions or divisions. Okay. So in other words, the expression you get from doing such integration just don't make sense. Okay, so the integration, so the result from these diagrams not well defined. Okay. Something's happening. So so the result is not well defined. So normally when we encounter divergences, we always tell students when you encounter divergences, of course, maybe one obvious reason is that you did something wrong. Okay, you just made a mistake. But if you have done everything right, when you encounter divergences, actually that's opportunity. Because each time you see a divergence, then that means there's something you don't understand about physics. Okay, if you understand, by definition, physics should not have divergences. Okay, so if you understand everything well, so divergences, it's mathematics tell you there's something, there's some important physics you are missing. Okay, so indeed, so here, so when you look at those divergences, you can say, oh, what physics are we missing here? So the physics missing here is very simple. Okay, the physics missing here is very simple. Because these integrals, because the divergent region corresponding to those quantities go to infinity. So those quantities go to infinity corresponding to have very high energy, very large momentum. Okay, in other words, from very short distance physics. Okay, but very short that comes from. So this comes from divergences come from naive extrapolation let's say consider QED to arbitrarily high energy scales. Yeah, because we use the framework of QED, but then when we do this integration involving very large momentum, okay? But nobody actually tells us that a QED should be valid at those very high energies, because the real experiment, you cannot probe very high energy process or very short distance. and because it's the limit of our energy resolution. Okay. So there's no reason to trust actually QED should be valid for K0 and K goes to infinity. Okay. Yes.
Is the divergence like the result of a problem in like perturbability expansion, or is it a problem with like the original
Yeah, it's not a feature of the perturbative expansion. Yeah, it's a genuine.
So it's like a legitimate problem.
Yeah, it's a legitimate problem. Yeah, it's a legitimate problem. Okay. So this divergence just comes from we extrapolate QED to arbitrary high energy scales. Okay. So you say, okay, then what do we do? Okay, then what do we do? So the simplest thing you can do, you say I only can measure. So suppose suppose in the 30s, in 1930s when people first encountered this problem, and you say okay, and then let's put a cutoff here. Let's only include the energy regime which we can access. Okay, but again, what cutoff you put there? Okay, so it's not clear what kind of cutoff you put there. What is the validity of this series? So ideally, you should put a cutoff there to add the boundary of the validity of the QED. Okay, but before you actually can probe the scale which QED breaks down, and which scale should we put there? So we don't know. Okay, so for many years, people thought this just doing this kind of diagrams just don't make physical sense. Okay, because we don't know the short distance physics. We don't know the short distance physics. And indeed, and this point of view was justified. So for many years, people just, for some years, people just gave up on these ideas. Okay, they just say maybe this does not make sense. But then after the Second World War, in the late 40s, and then a few young physicists at the time, Schwinger, Feynman in United States, and Tomologa in Japan, they say, okay, even though there are this kind of divergences, and even though we don't understand the short distance physics, let's see whether we can just use brute force, try to design some mathematical way to get rid of those divergences and see whether I can get sensible results. Okay? And so that was their starting point. And that was their starting point. And it was a crazy starting point because the physical reason for those divergences are very clear. Okay? And but then it turned out they actually success, but they managed to be successful. Okay? So in 1940, late 1940s, so you see people like people find the method. Yeah, so Feynman, Schwinger, and Tomologa. Okay, I managed it to find a way to remove the divergences. And get a physically sensible answer from such diagrams. Okay. And also, at the beginning, their work were very complicated, and very few people actually understood them. And Feynman used Feynman diagrams. Okay, so he invented the Feynman diagrams to do this. And because previously people do those calculations, they don't use Feynman diagrams, and they use very complicated perturbation theory, as you do in the non-relativistic physics. It's very complicated. And actually, that's what the Schwinger and the Tomologa, they were doing it. Okay. So at the beginning, the thing was very complicated, but then the Freeman Dyson, soon afterwards, he understood all their work and actually greatly simplified the process. And actually, the current understanding essentially came from the simplification of the Freeman Dyson. And then Freeman Dyson actually operated a Feynman diagram. In fact, Feynman diagram training essentially operated the Feynman diagram training camp at the Institute for Advanced Study when he was a member. So people went through there. They all learned this Feynman diagram techniques from Freeman Dyson, and then they spread it out to all other places. That's how Feynman diagram techniques got spread out, like in the physical community. Okay. And anyway, so Feynman Dyson he simplified the process, and then people eventually understood. Okay, and there is a well-defined mathematical procedure. You can actually get rid of those divergences and get a sensible, a physically sensible answer. Okay, and so it was a funny story because, and so this is called the program of renormalization. Okay, the process of getting rid of the divergences. And this is a funny story. It's because I said that there's a very physical, this is a very funny story for the following reason. As I mentioned, that we do know where the divergences come from. Okay, divergences come from our lack of understanding of short distance physics. And normally you believe you can only cure the divergence if you understand that physics. Okay, if you don't understand that physics, how you cure that divergence? Okay, so that's what most people thought at the time, including all these quantum mechanics big shots. Okay, all these old people like Dirac, Pauli, all those giants of quantum mechanics. They all believed you have to do something radical, okay, to QED. Otherwise, QED cannot be made sense. You have to invent some completely new formalism and to circumvent those divergences, etc. But then Dyson later commented that then those young people at the time, they say we were conservative. We want to just to look at those calculations, just want to make sense of those calculations. We don't think of those grand physics. I just want to make sense of those calculations. And then they succeeded, okay? And so this is an example which very old people, they want to do grand new physics. Okay, but young people want to very do conservative physics, just do calculations. One calculation at a time without clear physical motivation. Okay, but those young people turned out to be correct. Okay, and so they came up with this program. Yes.
So like, how does he know that they succeed by using calculation results more accurate than the G-level diagram, and like how much more accurate?
No, it's not about accuracy. It's about finding a sensible way to hide the divergences. Yeah. It's you can. Because today we'll not be able to go into the detail. I'm going to only tell you the result. It said they. So that's why their result was actually radical in some way, because they realized there is some way. Somehow those divergences, even they are there, they do not affect those observable physics. You can measure. Okay, they don't affect those things. So you can find some mathematical trick to remove them. Okay, and yeah. Okay, so yeah. But for many years, so after they succeeded, so this is late 1940s, and the Dyson was also late 1940s, early 1950. Even though this QED achieved. Yeah, and then as I'm going to mention at the end of today's lecture, and then the first calculated quantity is this anomalous magnetic moment, which now require doing a calculation of this one. Doing a calculation of this one, and Schwinger did the first calculation, and then he calculated, okay, the correction of these to the magnetic moment of electron, and that agreed very well with experiments. So that was a triumph at the time. Okay, so the experiment verified their success. Okay, but still, many people didn't believe this actually was something sensible. Many people for many years people thought this is just a mathematical trick to get some answer. Okay, and so many people still for many years people was doubting this program of renormalization. And then only much later in late 1960s or 1970s, when Ken Wilson came up with this idea called the polarization group, and then people finally understood the physical reasoning and the physical basis behind this program of renormalization. And yeah, so that was a revolutionary progress made by Wilson. Yeah, so all this will be covered in detail in quantum field theory too. Okay. And so today, let me just very quickly tell you what these loop diagrams do. Okay, what these loop diagrams do. So first, let me make some general remark. So mathematically, you get the divergences, and then you have to find a way to get rid of the divergences. And physically, there are also some new features, new important conceptual features. Okay. Any questions on this? Okay. So the first feature is that they already I already mentioned when you include such loops, you essentially include quantum fluctuations. Of the vacuum. Okay, so all this process, so those electron pair, that photon, and that photon, they're all some virtual particle just come from the vacuum. Okay, it just from the vacuum fluctuations. So you can actually show mathematically rigorously, okay, that the tree-level diagrams, any tree-level diagrams, can be obtained from solving your equation motion perturbatively. Okay. So just take your take your nonlinear equation motion. Okay, take the QED. You write down the nonlinear equation motion, and then you have this coupling E, and then you just solve that equation perturbatively order by order. And turns out all tree-level diagrams can be understood from that process. Okay, essentially just coming from solving your classical coming from solving that equation motion. But then we know that the quantum nature comes from doing the path integral. Okay, equation motion captures some classical physics, but the genuine quantum physics come from doing the classic path integral, which you integrate over all possible configurations. And so that is not captured. Okay, so those features of path integral is not captured by the tree-level diagram. But you may ask, does tree-level diagram actually captures any quantum physics? Of course, it does capture quantum physics, because all this notion of the particles, even the notion of the quantizing the particles, that's already including the quantum effect. Okay, it just the tree-level diagram does not include the fluctuations from the vacuum. Okay. Good. And so this is first feature. Okay, so when you include the loops, you actually now finally include the quantum fluctuations. And the second feature is very important, is that the physical mass, charge, and the field, and the physical fields are not the same as that appearing in the Lagrangian. Okay? So let me elaborate what this means. So remember, when you write down the Lagrangian for QED, you have I psi bar gamma mu partial mu minus IE a mu psi minus m psi minus 1/2 f squared. Okay, so that's not Lagrangian. And we say that this is the charge of the electron, and this is the mass of the electron, and this psi is the denotes the electron field. Means that when you act it on the vacuum, you can create the electron or anti-electron. Okay, and similarly, a mu corresponding to the a mu is massless, and when a mu acts on the vacuum, you can create the photon. Okay, you can create the photon. But it turns out that when you include the loop effect, the mass we actually measure. So by physical mass means the mass of the electron we actually measure in the lab, and the charge we actually measure in the lab, they're no longer the same as the one appearing in the Lagrangian. So the one in the Lagrangian should be just viewed as some kind of parameter. And so and your physical mass and the charge are functions of those parameters. Okay. Now there's a more complicated relation between those parameters and your physical mass and the charge. And also the physical field which actually creates the electron is no longer directly given by this psi. Okay, it's related by psi by some relation. Okay. So this difference, okay, so this difference is also called renormalization. So here there's two sense of the renormalization which actually used for completely two different contexts. So so this renormalization just means the removal of the divergences, and this renormalization means that the parameters in your Lagrangian may not be the same as the physical mass and the charge you measure. Okay, so the thing you measure actually it's related to the parameters in the Lagrangian in a non-trivial way. Okay, and this renormalization is in principle not due to the divergence, it's just due to the interactions. So heuristically, the physical is as follows. Just imagine you have a free electron. So if you have a free electron, and then the mass of the electron, then it is what you measure. Okay. But now if you include the interactions, and now electron can interact with the photon in a complicated way, and that interaction then can change the mass of the electron. Okay. So that's why. In general, for interacting theory, what appears in your Lagrangian, they don't have to be the quantity you actually measure. Okay, because the interactions can change how you translate those quantities into the physical quantities you measure. And so this renormalization just means that the renormalization changes over the value of your parameters. Okay. So now let me just make this a little bit more explicit. So before I do that, do you have any questions? Yes.
Looking at QAD in like by itself in going into the theory, what reason do we have to kind of assume that this parameter m corresponds to physical mass? Like, I was confused with how this is. I know the Higgs mechanism is how we say it gets mass and so forth.
Yeah.
But you're saying that QED on its own has its way of explaining how this parameter m relates to the physical mass?
Yeah, yeah. So this is the so when I write down this Lagrangian, and then I have a parameters here called E and M, and so if I ignore the interaction, when I ignore the interaction, and then the M will be the mass of the particle you actually measure. But now when you include the action, then the interaction can change that mass. It's not related to that Higgs story. The Higgs explains where this M comes from. Yeah, Higgs explains where this parameter comes from. Yeah. So this is a realization on top of that. Good. So now let me just elaborate what this means. Okay, elaborate what this means. So for this purpose, now let me put a subscript B here on everything, just to emphasize that they're no longer.
Can I ask one question?
Yeah. Yeah. Yeah, yeah. Yeah, yeah. Yeah, yeah. It changes the energy you need to create the particle. Okay. So now I denote everything to be with a B. So those are called the Baer parameters. So EB is called the Baer charge, and NB is called the Baer mass, and this psi B and A mu B is called the Baer fields. Okay, they're called the Baer fields. And when I write this F squared B means that the F squared constructed out of A mu B. Construct out of A mu B. So now let's just illustrate this thing using these three simple diagrams. Okay, so let's look at first that diagram. The propagation of electron. Okay, the propagation of the electron. So I will not. Yeah, you can just calculate. What you need to do is you calculate this diagram, and then you find the correction to the propagator. Yeah. So this diagram will induce a correction to the propagation, to the propagator of the electron. Okay, to the propagator of the electron, and from this correction, and then you find that the So let's first write down the tree level propagator. So this is given by -1 ik slash minus m plus f. Okay, so this is just mb. Okay. Okay. So you can interpret the mass of electron as the pole of this k. So when k slash equal to mb, and then that corresponding to the mass of the electron. Okay, and the mass of the electron corresponding to the pole of this propagator. Yes. Oh yeah. What I mean is just when you invert it, so this becomes k squared plus m squared minus epsilon. Yeah, it just means k squared equal to m. Yeah. So upstairs you have k slash plus m. Yeah, it just means k squared plus m squared. Yeah, just essentially the mass electron corresponding to the pole of the propagator. So now when you include such corrections, and then you find your propagator modified into the following thing: z divided by ik slash minus some other mass plus epsilon. Okay, and now this m mass is no longer the same. So this physical mass is now just mb plus something else, plus some correction. So this is the physical mass. So this tells you that the mass of the electron, when you include such diagram, actually get shifted. Okay, get shifted from your bare mass. Okay, from the bare mass. So if you naively calculate it, and then you find this correction is infinite, okay, you find the contribution of this diagram is infinite, and so that's why you need to include this normalization, etc. And then to calculate the finite quantity of this delta n. So you find that this the pole of the propagator change. You also find actually the residue also change. So here the residue just 1. Okay, here the residue becomes some other constant z. Okay, so that means that when you act psi b on the vacuum, you no longer create just the k. Okay, here I'm just writing schematically. You're actually creating square root z times k. Okay, because of the prefactor. Okay, so remember our previous psi b is equal to a dagger, etc. When you act on the 0, you will create a particle normalized in a certain way. But now with this z factor, and now you create not the factor. Now it's a prefactor z. Okay. So we normally define the physical field as the one which psi, when you act on the vacuum, which just precisely created the state. Okay, create the state. And so now there's a relation between this bare field and the physical field. Okay, and now there's a relation between the bare field and physical field through this factor. Okay, this factor. So this tells you that the field itself also gets the magnitude of the field itself also gets renormalized. Any questions on this? So the similar thing is happening for the photon case. So if you consider this process, so this corresponding to a modification to the photon propagator. So this creates a propagation to the photon propagator. So now you find that actually the photon mass is not changed. So even when you include such corrections, the photon is still massless. So remember, previously we say why you cannot add a mass to a photon. Do you remember why we cannot add a mass term to the Maxwell field? The gauge invariance. So the fact that the mass cannot be generated by such correction just means that the gauge symmetry is maintained. Okay, so the photon remains massless. But you do have similar renormalization of the strength of the Maxwell field. So now the bare field is related to your physical field through some factor. Called normally called Z3. Yes. Yeah, it's just a constant. Yeah, because we just calculated the this is just a constant. So this is defined to be the residue of the pole of the propagator. Good. So finally, let me mention a little bit the last diagram. So the last diagram. So this last diagram, which let me redraw it here. So remember, if you just have the original one, and then here is just IEB gamma mu. Okay, and now when you add such a correction, so this is the tree level one, and then at one loop level you can add such a thing. Okay, when you add such a thing, and then you renormalize the charge. Okay, then the charge gets changed. Okay, so now you find, interestingly, you find now that the new electric charge is related. So this is the measured charge, physical charge. Okay, through a complicated calculation, you find this physical charge is related to the bare charge by the same factor Z3 as in the case of the relation between the bare field and the renormalized field. Okay, you find that the same number so appears in the relation between the physical electric charge and the bare charge. Okay, the bare charge. So this is important for the following reason. So now you observe, because of these two relations, okay, because of this relation, that you observe that EB, A mu B, is actually equal to E A mu. Okay, so the product is the same. Okay, yeah, because the square root 3 factor cancel. Okay, a square root 3 factor cancel. Right. And this is important because of this. That means your covariant derivative does not change. Does not change. So remember, this the structure of this covariant derivative is needed for the gauge invariance. Okay, it's needed for the gauge invariance, and so that this is maintained. Again, it's an implication that the gauge symmetry is maintained. Okay, the gauge symmetry is maintained. In other words, you want to say that if we want to maintain the gauge symmetry, then EB and A mu B, they have to renormalize in the opposite way so that this is the same. So this is the same. So this diagram have two effects. So this diagram have two effects. One effect is correct the electric charge, and another effect is generate the magnetic moment, generate the new anomalous magnetic moment. So this has two effects. The first effect is to renormalize, to change your charge, and the second effect is generate an anomalous magnetic moment. Okay. So you may have learned in your quantum mechanics. So you may have learned in your quantum mechanics that anomalous has a magnetic moment which is normally written as following: mu E equal to minus E divided by 2m G and the spin operator. Okay, just because the electron has spin half, and so has a magnetic moment. And this spin half, of course, is normally written, this spin operator, it's in the spin half space, then just a sigma matrix. Okay. And this G factor, so this is a G factor which relates the, G is just a number. Okay, G is just a number. So normally called G factor. Yes?
Diagrammatic expansion is a perturbation theory empowers it.
Yeah.
So, like, you're saying you added a term and you change E?
Yeah, the E can change itself, yeah. So you just shift the value of E, right? Yeah, change is also small. The change is a higher order, yeah. Yeah, but this is a very good question. This is a very good question because naively, as I mentioned, naively, if you look at those corrections, say this delta M and this change between E and EB, they're all divergent. Okay, so that's why they're all very complicated. This all divergent, so that's why it's non-trivial to find the scheme to make sense of those equations. But you have all those divergences flying around. Other questions? Yes?
What is the difference between square root of z and square root of z?
Sorry?
What is the difference between square root of z and square root of z?
Oh, they're just different numbers.
Oh, okay.
Yeah, so this is one number, this is some other number. Yeah, just say electron field renormalized in a different way from the photon. But somehow the charge have to be renormalized in the same way. Yeah, but that's come out from a high. If it come out from the, you may say just come out from the gauge symmetry, from the requirements of gauge symmetry. Good. So this G factor. So the Dirac equation, one of the trump of the Dirac equation, when Dirac first written down, is that the Dirac equation predict that G equal to 2. Okay, G equal to 2. But in reality, in the late 30s and early 40s, the experiment were accurate enough. At the beginning, people thought G equal to 2. Okay, so that was considered to be trump of the Dirac equation. But then later, when the experiment become more accurate, they find that G is actually slightly greater than 2. Okay, of course, this accuracy is right later. At the beginning, they in the 40s, they can already see that the G is no longer 2. Okay, there's some small corrections. So there was a big question at the time. How do you calculate this correction? Okay, how do you calculate this correction? And so that amounts to calculate this diagram. So that's what Schrödinger did. And so he calculated this diagram. He managed to get rid of the divergence, and he managed to reproduce these small corrections. Okay. So he managed small corrections. So now let me just very quickly tell you where this result come from. Okay, where this result come from? Why the Dirac equation predict the G equal to 2? Okay, so this actually I had some point was thinking as a homework exercise. But never got to put it in the homework. But it's an instructive exercise, and so during the now let me try to explain where it comes from. So we have the Dirac equation. So now let's consider the Dirac equation. Of an electron coupled to, say, to some gauge field, to the electromagnetic field. Okay, so let's consider this equation. So the claim, okay, so the claim is that if you take this from this equation, of course, we don't see anything about the magnetic moment. Okay, we don't see anything about magnetic moment. So the claim is that if you take this equation and go to non-relativistic limits, okay, if you go to non-relativistic limits, you will get the Schrodinger equation. You get the so-called the Pauli equation. So you get the Schrodinger equation, and with a spin half particle and with a magnetic moment precisely given by G equal to 2. Okay, precisely given by G equal to 2. So now let's try to see this. Okay. Do you have any questions? So this is just the Dirac equation itself. But now if you include that vertex corrections, and then that will generate this additional term. Okay. So now let's look at this non-relativistic limit. Right. So we want to, so remember the Dirac equation as was originally conceived was already an equation of the Schrodinger type. Say have the form of the IHT psi equal to H psi. So you just multiply the gamma 0, I gamma 0 on both sides, and then remove everything away. Okay, so just this side keep only I partial t. So through that procedure, you have H is equal to m times beta plus alpha p plus EA, then plus EA0. Okay, EA0 is the 0 component of A, and EA is the vector component of A. So the beta is just the minus gamma I gamma 0, and alpha I is equal to minus I gamma 0 gamma I, and P equal to minus I. Right, just standard gradient operator. Okay, so now the claim is that if I want to take the non-relativistic limit, this equation becomes an ordinary Schrodinger equation, and including the magnetic moment. Okay. So this is clear what we want to do? Okay, so now let's choose the basis for the gamma matrices. So for this purpose, when you go to non-relativistic limits, it's convenient to use this basis, which actually I wrote down at the beginning when we talk about the Dirac equations. Okay. Again, 1 is always 2 by 2 identity matrix. So from here, you find that the beta just equal to 1, 0, 0, minus 1. And the alpha just become 0, sigma, sigma 0. Okay. So to reduce, right now we just choose, and then also let's write psi in terms of the 2 components. So each of phi and the chi has 2 components, altogether 4 components. Okay, so let's write psi in terms of 2 upper components, 2 lower components. So now let's plug all this into that equation. Okay, all this into this equation, and then we get partial T phi equal to m phi plus sigma dot p plus EA chi, then plus EA0 phi. Okay? And then for the equation for chi, you get a similar equation. But here is minus m chi plus sigma dot p plus EA phi plus EA0 chi. Okay? So you get these two equations. Okay, so now, so far we haven't done anything, okay? We just write this equation in a different form. So now let's consider the non-relativistic limit. Now consider the non-relativistic limit. So in the non-relativistic limit, this P, so this is essentially the momentum, spatial momentum. Okay, if you act on the wave. And so we take it to be mv. And of course, v to be much, much smaller than 1. Okay. And then this EA0, which has a unit of energy, so it should be of order mv square. Okay, should be order mv square. And this EA, which should be the same order as P, and then EA should also be of the same order as mv. Okay. Okay, now let's look at this non-relativistic limit. So far I have not done anything. I just specified this. And now let's consider a transformation. So in the non-relativistic limit, we know that your total energy so remember, a typical wave function is always the time dependence, say, always have something like IET, okay? And in the non-relativistic limit, E would be m plus 1/2 mv squared, etc. Okay? So this is much, much larger than this term. Okay, this is much, much larger than this term. So in order to so we can just isolate this bigger piece, okay? So we can try to isolate this big piece. So we will make a slight transformation. So we write phi equal to expansion minus IMT, capital phi, and the chi equal to IMT x, okay? This or capital chi, okay? So now this will only contain this low energy part, okay? So those fields will only contain the low energy part that already isolated the big things in here. Okay. So the time dependence here will only include the low energy part. So we assume that partial T phi, say, would be mv squared, say phi, similarly with x, okay? Similarly with x. Okay, so this is the fast oscillate part in time. This is the slow part in time. So now we plug this in to these two equations. Okay, plugged into those equations. Then we find I partial t. Yeah, I will also introduce I partial t phi equal to sigma dot pi x plus EA0 phi, and I partial t x equal to 2 minus m x. Yeah, let me just call it x for simplicity. Okay? So I also have introduced the notation that the pi is equal to P plus EA. Okay. Okay. So now you see the difference between these two equations. So they have mass term here have opposite sign. When I isolate that piece, and then the mass term for this equation cancelled. But in this equation, they add together, get this minus 2m. Okay? They get this minus 2m. So now let's look at the magnitude of each term in this equation. So this is like mv squared x. So this is like m times x. So this is just something phi. We don't need to work. We don't know the relative magnitude between x and phi. And so this is also mv squared x. Okay, we said EA0 should be of order mv squared. So these three terms, they're all related to x. And this term dominates over these two. Okay, so you can forget about these two terms. Okay, in the non-relativistic limit. And then we get, so from here, if I call this equation 1, and this equation 2, and from 2, we get in the non-relativistic limit, we just get 2mx plus sigma pi acting on phi equal to 0. Okay? So we now we find that x, we can now solve x in terms of phi, 1 over 2m sigma dot pi phi. Okay. So now we can plug this back into this equation. So this is equation 3. So plug 3 into 1 again. Then we get a Schrodinger equation for phi. So x is no longer independent field. It's just expressed in terms of phi. So now we get the equation for phi. Okay? So now you see each term, they are of the same order of magnitude. So this is mv squared. And this is mv, so upstairs pi is of order mv. So this is m squared v squared divided by m. So this again is mv squared. And EA0 is mv squared. So now everything is non-relativistic and of the same order. Okay, so now let's look at the meaning of this term. Now let's look at the meaning of that term. So that term, you can write it explicitly. Okay, sigma I pi I, sigma j pi j. But remember, pi I and pi j, they are operators, so you need to keep the order in them. Okay. Yeah. So we can just write down. So we just have sigma I, sigma j. Just give me delta ij plus I epsilon ijk sigma k, and then pi I, pi j. Okay? And so the first term give me the pi square. And the second term I can just using the anti-symmetric in ij, I can write it as epsilon ijk, sigma k, and pi I, and pi j. Okay, so I just write the commutator in terms of them. Okay. So now you can. Now it's easy to calculate pi I, pi j. So this is just minus partial I plus EAI and minus partial j minus I partial j plus EAJ. So if you calculate the commutator, you just get minus EFIJ. Okay? And now if you plug this Fij into here, so epsilon ijk times Fij, what do you get? You remember when epsilon ijk multiply Fij, what do you get? You get B, yeah. So now this equation, when you plug this in here, and then this just become pi square plus, just make sure. E sigma dot B. Okay? E sigma dot B. Because Fij multiply the Fijk, just get Bk, and Bk sigma k just sigma dot B. Okay? Yeah, it's 1/2 epsilon ijk times Fij give you B. Yeah, so if you use 1/2 epsilon ijk Fij. Okay. Okay, good. We are there. So now we are done essentially. So now the Schrodinger equation. Now we get partial t phi equal to h phi. Now h is equal to p square. So now you have pi square. So pi square, if I write it explicitly, is p plus ea square divided by 2m. Then plus e divided by 2m sigma dot b come from this term. And then the last term is EA0. So now if you recognize this part of the Hamiltonian is precisely what you get when you couple Schrodinger equation to your electromagnetic field. Okay, you have you just add P plus EA for the vector potential, and here you get A0. But now here you get additional term, so this is called the Pauli term. Okay, when the particle have spin, have magnetic moment, then you have additional term. So this term can be interpreted. So remember, when a particle have a magnetic moment, so when a particle have magnetic moment, then you have a piece corresponding to mu dot B. Okay, so if you compare this with that term, then we conclude that the mu, so in this case, compare that term will be equal to E to m sigma dot B. Okay? So now we conclude, from here you can read what's the mu. Mu just minus E divided by 2m times 2 times sigma divided by 2. Okay, so if you compare with this, and you find that the G is exactly equal to 2. Okay, you find G exactly equal to 2. Okay? And so this way you see actually the Dirac equation contains the information that electron have magnetic moments. Okay, have magnetic moments. Yes?
Is this okay from taking the non-relativistic to Dirac equation? Did we expect a G equals 2 for all fermions then?
Yeah.
Even if we look at these like perturbative calculations, like the 1 plus 0.001, etc., that should apply to all fermions as well?
No. Because the correction can be different for different fermions. Because different fermions, they have different interactions. And so that will change this vertex different. For example, muons and electron will be different. Yes? Yeah. No, in the high speed, you can no longer. So when you have high speed, all these effects, they mix together. So relativistically, you can no longer isolate the contribution from that angular momentum from your orbital angular momentum, spin angular momentum, they all come together. Yeah, so only in the non-relativistic case you can isolate like this. So normally when we talk about magnetic lower moment, we all think about in terms of non-relativistic situation. Okay, so now just some final words. Okay, just erased that number. So Schwinger then did this calculation. So including this diagram, Schwinger did this calculation, and then he found that there's a small correction. So normally it's called, say if I called 1 plus f, and so this is the correction, okay? And then the correction which Schwinger first calculated is given by alpha just divided by 2 pi. Okay, the reason is alpha is because here there's a e, here there's a e, so e squared just alpha. Okay, and then so all this complicated calculation you do, essentially you find this 1 over 2 pi. Okay, because this correction has to be proportional to alpha, and then this number you do a very hard calculation, you find this 1 over 2 pi. Okay, and then this actually agreed with the experiment very well. Okay, so this is first calculated by Schwinger in 1948. Okay, so this was really a chunk, a theoretical chunk at that time. Okay, and agreed very well with experiments. So then people then calculate to higher orders. So at the next order, so must be proportional to alpha square. So we can parameterize by alpha divided by 2 pi square, and then with some number A2. Okay, you do an even more complicated calculation, much more complicated calculation. You find that this A2. This, again, is a single number, and this contains 7 diagrams. So this is one diagram, but when you go to the next order, actually involving 7 diagrams, and that was calculated in 1957. Okay, again, was a very important thing to do at that time, because just to check whether QED, because the experimental accuracy was at the level, actually you can compare this number. Anyway, yeah, actually there's also there's some kind of story behind this number, which at the beginning they calculated wrong, etc. Anyway, so now you can also calculate the next one, A3. You can parameterize again by cube, and now this include the 72 diagrams. And then take 2 physicists. Yeah, I won't write down their names because took them 25 years to calculate it. So actually, they used it by some. So in 1996, okay, the Faraday calculated this. But now, if you want to say, oh, let's try to calculate A4. So this includes 891 diagrams just in QED. And actually, this is also calculated as in using computer. Okay. Anyway, and also you can calculate this for muon. Okay, muon will have different muon. They receive at a certain level. You also need to include the contribution from other interactions, not just QED. Okay, weak interactions, etc. Anyway, so the reason you want to calculate such a number to very high accuracy is because this F can be measured to very, very high accuracy experimentally. So actually, experimentally, this is one of the most accurately measured number in physics. Okay, they can measure this F, say to order 10 to the minus 12. Okay, 10 to the minus 12, and yeah. So it's a yeah. So I think the theoretical level you can actually cannot calculate to this level accuracy, but still you can compare to very, very good agreement. So QED actually describes nature very, very well. Okay, very, very well. Okay, so I think that's that's all. And yeah, I'm honored and very happy to have this opportunity to take you to this first part of the journey to quantum field theory. And I want to thank you all for making this journey very enjoyable and rewarding for myself. And I hope you have learned something from this class. And whatever your career path takes you, and I hope you will later find this course useful. Okay, thank you.